Let's look now at expressions for the input resistance and the output resistance for this circuit. And I'm not going to do the actual derivations from the small signal model. You can go ahead and do that as an exercise, or you can take a look at the textbook and see how they are derived. For now, we're just going to be using the reflection rule, and so we'll come up with an expression for the input resistance Rin, as well as the output resistance, which is now looking from the output terminal, which is now the emitter. For Rin, we can see that we have R1 going to an AC ground in parallel with R2 going to ground, so R1 in parallel with R2, and all that in parallel with the resistance looking into the base of the transistor Rib. And Rib, by the reflection rule we had said, whenever we look into the base of the transistor, we are going to see anything that is connected, any resistance that's connected to the emitter terminal, as long as we're looking from that side of the lens towards the right, it's going to be multiplied times a factor of beta. And that's called the reflection rule, and that's just because the current through the emitter is beta times larger than the base current. And so in this case, it's going to be times beta times, and I didn't draw it there, but we can see that there is the little Re, the dynamic resistance of the base emitter junction. And so we have little Re in series with capital Re. And for the output resistance, Rout, the resistance looking at this terminal, I can see that from that emitter node, I can see Re going to ground, and then in parallel with, and whatever resistance is going through that other branch. So Re in parallel with, and we have little Re in series with whatever is behind that base of the transistor. And now there is something called the inverse reflection rule, and what it tells us is that just like whenever we're looking through the base of the transistor from left to right, we are seeing everything, all the resistances multiplied times a factor of beta. When we're looking in the opposite direction through the same lens, we're going to see any resistances that are connected to the base divided by a factor of beta. And so this is going to be plus 1 over beta times whatever resistance is connected to the base, which is going to be R1 in parallel with R2. And that's it. We've come up with expressions for small signal gain, input resistance, output resistance for the common collector amplifier. I mentioned earlier this circuit is also known as an emitter follower, and the reason for it is simple. It's because the small signal gain is approximately equal to 1, and therefore we can say that the output follows the input. And you may wonder why such circuit may be of any use if the output signal and the input signal have the same magnitude. And the answer to that is the input-output characteristics. This may become a little bit more obvious if we do a practical example. Thank you.